Our next speaker is Professor Ron from UC Berkeley. Professor, could you please share your screen? Professor Ferring is a pioneer in bio-inspired robots. He mentored many distinguished researchers in our robotics community. Professor, the stage is yours. Thank you.
Okay, thank you very much. Thank you very much for the invitation. My screen shows up okay?
Yes.
Okay, excellent. Great. So I want to talk today about 2D fabrication for 3D milli-robots. I was very inspired by Professor Suzumori's presentation, and I thought I'd take this opportunity to kind of go through the history and show some of our trials and tribulations along the way. Let's go here. So I'll just start with a brief history, some of the designs we've taken, and basically lessons we've learned along the way as we've gone from, I think, very crude prototypes and proof of principles to some final designs which actually have pretty high performance in spite of being made with very low cost and imprecise materials. So we started way back in 1991 with Chris Piester's work, trying to figure out how we could take all of that wonderful planar MEMS work and make it a little bit more robotic by getting out of the plane. So by taking plates of silicon, polysilicon, fold them up, could start to make all sorts of interesting structures. Though, of course, the limitation at the time, we didn't have good joints, so a lot of friction. So the flexures worked fine, but not the joints. About 10 years later, we had this very interesting project to build a 100 milligram flapping flyer. And for some reason, I guess we decided that hollow beam structures, based on some of the things we'd seen in the polysilicon, would have a very high strength to weight ratio. So we were using stainless steel, which, as you'd think, is a little bit heavy, not the ideal material for a flying device, but turned out thin material formed in hollow beam has got pretty good strength to weight ratio. Well, that had a lot of fabrication challenges with it, and we after only about a year or two, came up with this much better process. With Rob Wood was the one who got us into this, using, instead of folding up stainless steel, using laminated carbon fiber structures. And that approach has been what we've been using over the last 18 years, using a laminated structure rather than stainless steel. So we've branched off into cardboard, which works very nice for quick and cheap prototypes. And just sort of an example here of the sort of the as far as we went with the technology back in 2003 with the quad flapper. So the overall design process, I won't spend very much time on that, just to highlight there's a lot of room here for improvement in coming up with automated design tools. Like Cynthia Sung had talked a little bit about that. It'd be wonderful to be able to just specify your design here, have it go through a panelized design, cut everything out, figure out how to fold it. But just to give an overview here, I think one of the critical steps is that with our prototyping technology, we have about a 3-hour cycle time from when you figured out what the design is, through cutting and folding. And I think that's been a really critical thing, because there's so many interactions between the dynamics and the materials and fatigue and delamination, that really having the mindset that we're going to build things, they're going to work for some number of seconds, maybe some number of minutes if you're lucky, and go back and figure out how to redesign things so that they're stronger and more durable. So one of the interesting lessons on this, we're making things with folding structures. We don't have pin joints. We have a lot of compliance that's intrinsic into the fabrication process. So we've ended up kind of thinking about things a little bit differently. When we started out, we really had a control robotics mindset that we need to build things that if I control my joint angle, the end of my wing will be where I want it to be. So we spent a lot of time trying to do that, and realize now that because of the way we're building things, I would say that the punchline here is with compliant structures, kinematics is a suggestion, not an imperative. And anytime your limb is working on something, whether it's the ground or the air, with these types of folding structures with flexure joints, it's really hard to get it to do exactly what you want it to do. So you have to just take a step back and say, well, we're going to design something and it's going to do what it's going to do as it interacts with the environment. And so it comes up with a different paradigm. I don't think it's completely worked out yet, but we're relying more on the natural dynamics rather than specifying exactly what's going to happen from a control point of view. So let's go through some of the folded stainless steel. We started with sheets of stainless steel, and in retrospect, this is just such a bad idea. But it was like, oh, monolithic. It's a monolithic material, isn't that isn't that a feature? Not really. In the end, we decided monolithic is not a good idea. But let me run through this. So we wanted to build these 4-bar structures. So it starts with a flat sheet, which is cut out. The first folding step is to fold these plates into triangles, and then the overall structure is folded up into, this would be like a little 4-bar mechanism. And the way it's fabricated is starting with a sheet of stainless steel, a row of holes is cut through for where the folds go, and then it's just folded up. And look at these. These are the joints. Joints are made of stainless steel. Hey, it's monolithic. That does not work very well at all because of the fatigue sets in. These mechanisms are designed to run at 100 hertz or so. So you really get fatigue starting in just a few seconds. So we wanted to keep the strength that we get from the stainless steel, the strength to weight ratio we get from the hollow beams. So we integrate in a flexure layer into the structure. And so this is actually only a year or so later from that initial crude design. New design, this is the folding structure. These are, again, 4 bars. Now there's a separate flexure layer made of polyester, so it's designed to flex. The other layer is, the stainless steel is designed to be very rigid. It's a good idea. There's some problems here as well, that these materials do not really bond very well, so delamination is a big problem. But in any case, through the sort of heroic efforts of the students at the time, like Joe Yan, Srinath Abedinullah, Rob Wood, we were able to build these pretty complicated structures. This is 2 4 bars driving a spherical 5-bar linkage here to give a 2 degree of freedom wing drive with 2 actuators. And this is showing the detail, 12.5 micron stainless steel shim, thin polyamide film for the wing, 6 micron polyester flexure. And so actually with stainless steel, you could build a structure like this. It looks like it's heavy, but it's hollow. So it's on the order of 100 milligrams. Showing that picture again. And we could see that this is a strobe light, so the wing is going at about 100 hertz. It's showing both a flapping and a rotation motion. That's what we expect from the spherical 5-bar. We wanted at the time to have independent flapping and rotation. They're actually very coupled through the dynamics, of the whole paper on that. But this mechanism, we put it on the end of a boom, so the gravity is balanced out, and we do get some flight forces here. You can see as the wing turns on, it can generate some lift forces. So it is kind of working. Very tedious to build this. Lots of super glue under the microscope with needles. One slip of the needle with a drop of super glue on it, and the super glue goes into the joint rather than into bonding the polyester to the stainless steel, and you almost have to start over again. So very, very frustrating after maybe 12 hours of laser cutting and 6 hours of assembly to have your design go with one slip of a tweezer or a needle. So luckily, that I guess the the frustration with that was the mother of invention. We switched to a carbon fiber process, much easier. The bonding in these things is with stainless steel is always a problem. So using a pre-preg carbon fiber, which has adhesive built into it, has just made things so easy. So now we take with carbon fiber, cut some holes where the flexure goes, add a polyester flexure layer, cure that, add a second layer of carbon fiber, laminate it up together, and really there's the assembly at this point is just aligning just aligning just aligning the top and the bottom layer of the carbon fiber and getting that to cure, and you're pretty well set. And then there's a final final folding step. So this is the structure we were working on. This is the micromechanical flying insect. It's got a modular set of actuators, 4 actuators, 2 for each side, that slide into this airframe. There's a slider crank which connects the piezoelectric cantilevers to this 4-bar. The 4-bar mechanism, then 2 4-bars combine together to drive this spherical 5-bar differential, which drives the wing. So this whole device weighed about 120 milligrams, no electronics, battery. Control was way in the future, I think, with Rob Wood's lab, probably almost a decade later with the actual control and making this thing work. But let me show you what the pieces involved. It's much easier than folding stainless steel. These are all laser cut pieces. You can see the very thin lines, which are the joints, the wings, the differentials, all this combined together into this structure. This was in 2003. Here's a slightly different version where the 4 bars are folded inside. So the center mass is somewhere at around this point here compared to a dime. And this is what it did. Again, we're lacking control, but you do see it certainly generates some pretty significant flight forces, at least compared to its weight. Okay. Well, along the way, we're realizing even the carbon fiber takes a long time to cut and cure, and we had another laser cutter available which could cut cardboard. So the idea came about, well, why not prototype some of these carbon fiber devices in cardboard first, and just get an idea of whether it's going to work, and not have to wait a long time for cutting and curing. Do something that you just cut out a laser, cut out the cardboard, apply adhesive layer, run it through a laminator, and have your device. And so we came up with this idea. Okay, we'll just use cardboard, poster board. Same basic idea, put a layer of adhesive in. Since it's not pre-preg, we could build joints. And here we can scale it very easily. This is the device we want to make, a little robot, make something 5 times bigger, just scale it all up in CAD. That's pretty easy. And along the way, as Carmel mentioned, we made a little shape memory alloy, a little self-contained robot. That was just a scale model. That's out of glass fiber. And it's got an onboard processor. It can turn left, turn right. It's got a little optical communications link. So that works kind of nuts. So sort of good proof of principle. But what we're thinking about is this cardboard is like, well, just for the heck of it, why don't we think about using cardboard? Why not? Why do we have to use fiberglass or carbon fiber? Why don't we try cardboard? So this is now about 7 years later, with many design improvements along the way, in particular coming up with strong joints, instead of using polyester, using ripstop nylon, which has a much more resilient, doesn't have the fatigue issues, or doesn't have any crack propagation, and we can actually get it to bond pretty well, so it doesn't have the delamination issues. And so then you could say, like, okay, well, let's see what we can do with cardboard, and let's just put a big motor on a cardboard robot, and see what happens. And just to tell you what's going on here, so we take a very high power to weight ratio, 120 watts per kilogram with a brushless motor. This is like a dragster robot. We've got other robots which steer. This one just goes straight. But it was the purpose of this was to see what are the limits of legged locomotion if you try to go faster than the limits that are set by the spring-loaded inverted pendulum model. And we can see this robot run through here. So its leg speed is at about 45 hertz. And this goes close to 5 meters per second. Next segment will show the video a little bit clearer. And what we found is that the motion just gets smoother and smoother. The power consumption goes really bad at higher power, but you can run now faster than at scale than natural animal would run. And we were kind of I think it was kind of fun. We did it with cardboard. We didn't need any fancy materials. So there's a lesson there that there's something in doing a design iteration, even with inexpensive, non-ideal components, if you have enough iterations and insight to make it work well. Right. And so just an overview of sort of what's going forward. If anyone's interested in this process, we have 2 versions of OpenRoach that are available. If you have access to laser cutter and a 3D printer, you can follow this process and build your own robot. And one of the other things we're thinking about, the sort of future project, is since we can do folding, if we can bring a machine along on our robot, we may be able to fold in the field, and we can generate parts on the fly. We call that the Robosome. So what are just some lessons learned? It's a little long here, but if you are going to be building these folding robots, delamination, it's like so much of our work in the last 20 years comes down to finding the right glue. So that's the key to robotics, at least in our lab, is good adhesives. For flexural robot design, kind of rigid legs, thin, short, resilient flexures, short and thin as you can get them. Murphy's Law comes in. If you need a simple flexure joint to act like a pin joint, it's going to buckle instead. It just that's the way the energy says it's going to do. We've really found this go with the flow is a really sort of philosophically, I think, one of the keys to the success of these robots. We underactuated. I think it's underactuated robots are underappreciated because they force us to not assume that we can overcome the natural dynamics. If we're underactuated, we're going to do what nature and physics says we're going to do, not going to be able to control around that. We think that actually leads to some efficiencies in the performance, like you saw with the X2 Roach. Passive tuning, again, the mechanics comes in. This is actually works to our favor, having a nice, lightweight, sort of compliant mechanism. Lots of failures, always lots and lots of failures. Having students who learn to appreciate that the failures are part of the process and not a reason to feel bad. Failures are, the more failures you have in the shortest time, the better you're doing. And as I was mentioning there, I think the high number of trials and design does compensate for non-ideal components. So with that, just leave this slide up here, and I think if there's any, thank you very much. And if you got any questions, I think we might have a couple minutes.
Yeah, thank you for showing those very lovely and very high performance robots and its fabrication methods. Any question from the audience? And you can either ask through the Q&A box, then you can talk with Professor Faring offline, or any way to that we can communicate in this workshop. I have one related question. For many flying robots, I think they are still based on piezoelectric actuation. Do you see a potential that we can leverage like a smaller miniature electrical motors for flying robots?
Oh yeah, actually, I've seen some things now with Professor Campolo in Singapore has been doing little motors. Xinyan Deng at our Purdue. So I think if you're willing to go a little bit heavier, like if you're willing to go up to 2 or 3 grams for a flapping flyer, the motors start to become, I think, pretty competitive. We also may see things with the dielectric elastomers. They could start to have good power density as well.